right, question number 3, he asked you to answer or the following questions based on this hill plot. So, how do we know it's a hill plot? Well, we should look at what's plotted on the axes here. So, on the y-axis, we have a logarithmic scale here, wherein I actually took the log, so the log is basically done for us. And it's the fraction and bound minus 1 over, sorry, it should actually say divided by, my bad, y over 1 minus y. That was a typo on my part. All right, on the x-axis, we have the log of the substrate concentration in micromolar. All right, so this question now asks you which protein has positive cooperativity, which one has negative cooperativity. So a non-cooperative protein will exhibit a straight line with a slope of 1. All right, and all proteins will basically have that same slope of 1 for their first ligand binding event. So that occurs at really low substrate concentrations. So these portions of the curves here correspond to the first binding event, and then also at the last binding event, because there's no longer an opportunity for one site to influence any others, they'll also have a slope of 1. Right. So the slope basically tells you about the gives you the Hill coefficient. All right. So as I said, for the first and last binding events, they can't be cooperative. All right. So the slope will be 1 in those regions. Now, in the intermediate regions, so the orange part is really obvious. It's right here. The blue part a little less so. But it's kind of right through here where the slope is different. All right. In those regions, all right, the slope again gives the Hill coefficient. Now, the question is, what is the slope there? Well, we'll focus on the orange case. So how do we figure out slope? Well, it's rise over run. Well, the rise is probably about, in this region, we'll say 2.5. All right. So we have a rise of 2.5. The run, the distance it traveled, is, we'll say, about half, so about 0.5. So the slope here is roughly 5. All right. That means the Hill coefficient is 5. So a Hill coefficient greater than 1 corresponds to positive cooperativity. So protein Y, the orange curve, has positive cooperativity. All right, let's look at the blue case. All right, it definitely has cooperativity as well. You can actually tell just by looking at it, because the slope is decreasing relative to the regions where it's 1, right? The slope is just going to be less than 1, and so that means it's going to have negative cooperativity. But let's go ahead and figure out what the rise over run would be. So our slope, basically we measure it from about there to there. The rise, I'll say, is roughly 1/2. All right, the run is about 2. So about have half over 2. All right, so this is about 1/4, or 0.25 for the slope or the Hill coefficient of that one. All right. Then actually we just did part D. So calculating the Hill coefficients is just the rise over run of that middle region between the two regions where the slope is 1. Right. So that's how you measure the slope of that region. You get the Hill coefficient. All right. Now, the only part we haven't done here is part C. Now, part C is perhaps the most challenging part of this conceptually. Now, the things to remember here are that the first part of the curve tells you about the first binding event. The last part of the curve tells you about the last binding event. So we'll focus on protein X here to start with, the blue one. All right, so there's our first part. All right, there's our second part. We can go ahead and draw straight lines and actually extrapolate those lines a little bit beyond the data points. All right. Now, again, the P50 value, the P50 is essentially the KD for hemoglobin. This definition of that is the substrate concentration that gives you half maximal binding. Well, when the binding is half, right, that means Y is equal to 0.5. Well, then, it is Y over 1 minus Y. Well, half over, if we have half, Y over 1 minus Y, right, this whole thing then becomes 1, right? So we want to look at the point at which those black lines that we drew cross a value of 1. And what is the substrate concentration at that point? So if we draw a line straight down here, we're going to get a value there. If we do it from here, we get a value about there. Well, right about here, we have a x value of about negative 1/2. Here at the top, the topmost portion of the curve, we have an x value of about, we'll say 1.5. Now, keep in mind now, these are log values, all right? So in order to undo a log, we have to do 10 to that power. So for the bottom part, we'd have 10 to the negative 1/2 power. For the top part, it'd be 10 to the 1.5 power. All right, so if I calculate these out, all right, 10 to the negative 1/2 is about 0.3, and our units are micromolar. All right, the 10 to the 1.5 power, all right, this is about 30, we'll say just round to 30 micromolar. So our first binding event for the blue curve has a binding affinity of about, or KD value, or sorry, KD or P50, I should say. Should actually be a KD because these aren't units of pressure. My bad. All right, we'll just do KD for now. Of about 0.3 micromolar. All right, the higher, the later binding event has an affinity of 30 micromolar. All right, so you can directly now see the negative cooperativity. So the first binding event is very strong. The last binding event is relatively weak. All right, now let's do the same thing here for the orange curve. All right, so we're going to take those regions where the slope is 1 and extrapolate them like so. All right, and we're going to find the region where they cross the value of 1 on the y-axis here. All right, where the y over 1 minus y is equal to 1. All right, so then we'll draw a line straight down, and then again straight down from here. All right, and so we end up right here with an x value of 0, and we take 10 to that power, so 10 to the 0th power is 1, so 1 micromolar for the first binding event. Or sorry, this is not the first binding event because it's corresponding to this portion of the curve, right, which is the last binding event. So last binding event has an affinity of 1 micromolar. The first one, we follow this part of the curve to here on down. All right, and so we get x value of about, we'll say 1.8 in this case. I'm just kind of estimating. So 10 to the 1.8 power is going to be about 63 micromolar. So our first binding event gives us this this portion right here. So our first binding event is given by the lower portion of the curve. Its binding affinity corresponds to about 63 micromolar roughly. The last binding event is found by extrapolating the top part of the curve, all right, and this has an affinity of 1 micromolar. So in this case, we're moving from a weak binding event of 63 micromolar to a tight binding event of 1 micromolar, and this corresponds to positive cooperativity. And that's it for number 3.